Hello guys, welcome to my YouTube channel, and today we are going to do a problem called path sum. This is a LeetCode problem. We will solve it in Python and Lua, and the problem is asking, also guys, I also made a script because I solved this already, and I'm just here to teach you guys how to solve this solution as well. Well, I drew as much as I could, but my handwriting's kind of horrible, so that's why I started drawing with what I could beforehand. Anyways, so let's read the problem. It says, given the root of a binary tree and an integer target sum, return true if the tree has a root to leaf path such adding up all the values along the path equals target sum. So what does that even mean? That means given a root, which we start over here, which is the top. So given a root value, let's say our root is going to equal 5. It says, and an integer target sum, which we will equal it to, let's use this example real quick, 22. That means from the root all the way down, so if we do 5 plus 4 plus 11 plus 7, what is that? This is 9, this is 20, this is 27. So then we would say, okay, once we get to this bottom floor, or this bottom root node, or once we get to the leaf node, then we would say, is this value that we calculated from going down this path equal to 22? If yes, then return true. You would have to calculate all these numbers. Let's say 22, this is, so once we calculate all these numbers, if we at least find one value that is equal to the target sum, then we would return true. So if one of these leaf nodes is equal to target sum, then we would get 22. So hopefully that makes sense, guys. So to solve this problem, we would need to know what a node is. So this circle thing is a node, and a node has, if we look at this, it has a left node and a right node. So I drew it over here. So if we say node at 5 without the left and right node initialized, then it will default to null. That means there's nothing in there. You can say none or nil. So that means if we make node 5, we will have none or nil. And let's say we make the root value equal the top one. So if we want a root of node 5, then that's how we would set the root of our tree. So if we made another node which is 4, and if you make a new node, it's going to have null and null, but we then say root.left equals node 4. That means, what this means is that we will make this 4 right here and set it to its root.left, which is root, dot left is going to equal to 4. Hopefully that makes sense. And if you're going to do if you want to set a right node, you just do root dot right, and then you would equal that to node, let's say 6 or something. Then just imagine that there's going to be a 6 here. And that's how you basically make a tree with nodes. And that's how you make this big tree with nodes. So this right here would be considered a leaf node because 5 has null and null as its left and right value. Now, if we look at this like tree, we can see that over here that this 7 has a left and right value of null. This 2 has a left and right value of null. This 4, it has null, but the left value is actually a node. So this would not be a leaf node. This would be a leaf node. This would be a leaf node. This would not be a leaf node because it has a right side value of 1. So that's why we only calculate these 4 values right here. You see, and so that's how we will start building our code. Once we find, we will basically traverse through this tree going left first, and then once you reach a node that has 2 null pointers as its left and right value, then we would say, oh, okay, since we've been like calculating like the value going downwards as well, we're gonna say, okay, does this, now we check, okay, since we reached the bottom value, does this equal our target sum, which is 22? And then you say no. Okay, so what happens if it's not the target sum? Then we would actually go backwards, right? But we will not add 27 plus 7 and make it 11. It's just going to like take it off the stack. So let's say our stack looks like this: 4, 11, and 7. Then it's just going to remove the 7 from our values list. So let's say we're like making a tree, right? We do 5. We start at 5. We keep going left until we hit 2 null values. Then we check for target 22. But we would do 5, 4, 11, 7. Then you keep checking. Okay, so let's say this is null. And also this is null. So if its left pointer and right pointer is null, then we would take we would check its value, which is 27, and does that equal 22? Question mark. And you say no, it does not equal 22. So then you would pop this 7 out of here, and now our thing is 5, 4, 11, which is 20 still. Okay. And then since we already went to the left side right here of 11, we haven't really explored. We went over here and that gave us 7. And then we said, okay, the left side is not 22. So we check the right side now. And then this 11 is going to go to the 2 value. We're going to see, we're going to check, okay, we checked 7. Now let's go to the 2 value now. And then we're going to check, oh, okay, does it have a left pointer first? So let's say this is the L. And then we would check the right pointer now. And that's equal to null as well. This left pointer and then the right pointer. And if that is equal to null, then we have reached our base case of what is the value of 22. Like, you know, 20 plus 2, since we've got the 20 from this stack already. So then we're like, okay, does 22 equal our target value? Like, does it equal it? And then we're gonna be like, yeah, we found it. So then we would return true. So what does that look like in actual code if we were to, code that? Well, first of all, test case in here is what if there is no root and our target sum is a 0? Okay, what if our root is like there's literally nothing in this array? There's nil. Null. There's nothing. Then if we have a target, it doesn't matter what the target is, like unless it is equal to nil, but our target over here says it needs to be an integer value of negative 1,000 to 1,000. So it cannot be nil. So that is why our first line of code would be to check if the root is going to equal null. And then we're going to return false if our root is equal to null. And that's our first case. And then after this, after we check that it's null, then we can keep going and check now, since we have a valid node right here. Since we have a valid node, we're going to have to check if this node is actually a leaf node. So we say, is it a leaf node? So what we do is check the left side if it equals null and the right side if it equals null. The next step we need to do is, since we have the target 22, what we can do instead of keeping track of like what 5 plus 4 plus 11 plus 22 is, plus 2 is, if we do 22 minus 5, that should give us 17. And then we do 17 minus 4. What is that going to be? That is going to actually be 13. And then we do 13 minus 11, and that is going to give us 2. And then we go 2 minus 2, and that is going to give us 0. So once we actually hit 0, then that means we know we hit our target, because every time we traverse, we just subtract instead of, add to get to the target value of 22. So in our code, we need to check if it's a leaf node, and also if the sums that we go to, like this pathway, target sum minus root value equals 0. So the root value is going to be here. This root dot value is going to be 5. So you do 22 minus 5, and then we're going to be like, okay, that's going to give us 17. So you do minus 14 again. What we actually need to do is we are going to keep on changing this target sum to be equal to where we're at in this pathway. So what does that even mean? So when we're at this 5 over here, we will be calling target sum. It is going to start at 22, but if we call our whole function has path, what we will actually be giving it is the root node, which is going to be 5. And honestly, I'm going to abbreviate this to HP. This has path equals HP. It's going to be HP and then 22. You guys see that? So once we get to this second value over here, we will actually be doing this, has path at 4, and then we're going to be like, okay, what is the new target going to be? It's actually going to be 17. So once we're over here, we're going to check it for 17. Once we're over here, we're going to check 22. Okay, 22 down to 17. And then we go here again, HP, but we're at 11 now. So we're going to check the root 11 node. 22 minus 5 is 17. 17 minus 4 is going to be 13. 13 minus 11 is going to be 2. 2 minus 2 is going to be equal to 0. So once we're in this function right here, at this HP22, we're going to be like, okay, so now our target sum is 2, and our root value is 2, and that's going to be equal to 0, so this is actually going to return true. Okay, hopefully that makes sense to you guys. So, how do we know if it's going to return true? Well, it's going to return true only if this is a leaf node and we have HP22. So that means if our leaf node, if it's an actual leaf node, which it means it doesn't have a left pointer and a right pointer, and also, you know, the sum of these four values is going to be equal to 0, then we would return true. Else, how would we call this recursively? Well, what we want to do is we look at the left side, like first, on what that equals to. Okay, so when we do root.left, it's going to be root.left right here. Let's use green. So root.left is going to be this part right here. This part right here. And then we would say, okay, so since we pass in 4 from, you know, in here now, then we do target sum minus root value, which is target sum right here. The target sum 22 minus 5, and that's going to give us 17. So that's why we do this for the left side. Okay, but we need to keep doing that. We need to keep going left, and that's why we do, you know, 17 minus 4 is going to be 13. 13 minus 11 is going to be 2. But since it's 2 over here, we would be like, okay, HP, if we keep going left over here, right, it's going to be HP, our root value, which is 7, and also 2. But 7 minus 2 is not going to be equal to, it's going to be like, it's going to be equal to 5, and 5 does not equal to 0. So then we would, okay, so then what? We're going to return like false here because the root is equal to null now. Okay. So once we get over here, it's going to return false. Over here is going to be false. So it's going to return false. It's going to return false here. Actually, it's going to return false one time here, and then it has to go back upwards. Once it returns false here, it's going to go back upwards. And then it's going to be like, okay, so how do we check the right side, right? So then you look at this. You do right, root.right. Okay. So if the root.right is going to equal to our sum, okay. So then it's going to be a root.right. What is that? It's going to give us an F. And that is not going to, that is just, if it gives us an F, it's going to go back up here. And then it's going to go back up here. And then it's going to try go to the right side. Hopefully that makes sense to you guys. And then now we can check if, alright, if the left side, if the left side returns false or false, then that means we're just returning, like, the whole tree is already evaluated. Okay guys, I was kind of confused on, you know, if this false and false thing, whereas then this is me in the future reading, like, you know, trying to understand my like problem or whatever. So when it goes over here, right, we're gonna hit null is going to equal null. And when the root is equal to null, if we're at 7 and we do root.left, this is going to return false. Then when we see that, okay, wait, we know what this is now. This thing right here, it's actually going to be false. So then, now we go to this right equals sum right here. So it returns back. It's going to be like, hey, 7, I know what the left side is. It's false now. Now you can compute the right side. Oh my gosh. So then it's going to be like, oh, okay, well, what is the right side? Well, we're going to give you the root right side from starting from the 7, right? And we're going to see like, oh wow, the root is going to equal null. So we're going to return false. Yes. And then it's going to be like, okay, well, go back up. Since now it's going to go back up to 11. It's gonna go back up to 11 and it's gonna see like, okay, so this right here, since we went left side already from 11, it did not calculate the right side. It literally, it, it did not calculate this right side yet. So we're going to go to the right side. Okay. And then that is going to be like, oh wow, the root is going to be 2 now. Okay, it's going to be like, okay, well, the left and the right root of 2 is going to be equal to true. So this is going to be equal to true, right? This value for 2 is going to be equal to true. And then it's going to be like, okay, this sum of 0 thingy, integral sum, is equal to 0 now. So then it's going to be like, wow, this is true. That's why it's going to have the value of t, but this, oh, it's because this side is false now. But anyways, this is going to be true now. So then now it tries to go back up. It's going to be like, okay, this is true. Okay, now this is true. And then now this is true. It's going to see the left side. It's gonna, now that it knows the left side is true right here, I think what it is going to do is, since we have a true over here already, we don't need to evaluate the right side anymore because T or F makes this always to true. That's why we have this left sum and right sum and this OR value. So we don't need to calculate this right side of the tree. So hopefully that makes sense, guys. Alright, let's start coding it in Python. We need to check if the root is equal to null first. Okay, if root is equal to null, or in Python it's called none, then we would return false. And then if, and then this is where we check if it's the root is going to be a leaf node. So that means if the root.left is equal to null, none, and root.right is equal to none, then we can just store it in a value, okay? We can say is leaf node. So is it a leaf node? Then we can say, okay, so since we checked if it's a leaf node, we now have to check if our value every time we traverse is going to reach 0. So is sum 0. So then we would say, okay, so we would do target sum minus root.value, since you know it's called self.value over here. Now we just check if these two conditions are correct. If we're at a 0 at the leaf node, then we would return true. If is leaf node and is the sum 0, then we would return true. Sorry. Needs to be capital. And then else we would, if it's not a leaf node and the sum is not 0, then we would keep traversing this tree. So that means we need to check the left side. And how we do that is we just send has path sum. You have to use self since we're using the definition class or the function. Then you can say root dot left side because we're checking the left side. And then we'd say target sum minus root dot value. Since we have to pass in the new value, which is 22 minus 5, and that's going to give us 17. Hopefully that makes sense to you guys. Okay, now we need to check right side. So if we haven't seen a leaf node and a sum 0, then we have to check the right side now. Root dot right, target sum minus root dot value. Then we can just return check left side or check right side. So it would return true, like all the way back up, if we found one true before. So this should work, guys. Oh, I need to make this equal to 0, sorry. So we need to check if this sum is going to equal to 0. There we go. Now we can just submit and see that it equals, you know, it's good memory, runtime efficient. What is the, oh, we haven't gone into big O complexity, huh? The big O time of this depth first search algorithm is going to be big O of n, which is the number of nodes, because we just check each node one time, right? And it's not going to like count it going backwards or whatever. It's just like, it's just gonna pop this off, and that's constant time, and just say it's gonna go like right here after, like straight in sync. It's gonna be like, okay, get rid of that, put this onto, just check the next right side or something like that. So that's why our time is O of n, and our space, it's actually going to be n as well. I think our space is going to be n because the only space that we use is these 4 numbers right here. So this is the only space that we're storing. It's going to be weird because we store like f at, we store this value, we store this value, we store this value, and then this value. And we don't store this value right here for memory because we don't even like bother of, well, we compute it onto the stack, but we're not like saving memory for it since we haven't reached the 0 target sum or whatever. So that's why our space would be n as well. It would be linear. And that's time and space complexity, sorry. I didn't go over that before. Okay, so how would we write that in Roblox? In like Lua, sorry. So what I had to do is I had to make my own tree, which is, we're gonna just have to set it's the same thing, but our root node is going to be starting at 5, and then the left side, so if we go root dot left, it's going to be 4, root dot left is going to be 11, left is going to be 7. So like after this 11, it's on the left side of the 11 is going to be 7, and the right side of the 11 is going to be 2. So that's like how I made this tree. And I can use this function called node, or I can use this kind of class-like structure, which has the value left side and then right side. That's why I'm doing these dots and whatever. But what's weird is that if we make a node like this, there's actually going to be a value there and it won't become nil. So that's why if our value is nil, then we would return nil. We would return the table if as our root, and if a root is going to be a table, then that means it's not going to return false, since it's going to be like, oh, there is actually something in the root. It's a table. But I just said value equals nil if there's nothing in here. You can also just think of root 3 as nil, then it would still work. But yeah. Alright, so to write our path sum in Roblox is going to be the same thing as Python. We just need to check if the root value is going to equal nil. Then we would return false. Now we do our now what we do is we check the leaf check if it's a leaf node, and also if the sum of the nodes that we go through is going to equal to 0. So local leaf, is it a leaf node? Then we say root dot left equal nil and root dot right equal nil. So if the left side is nil and the right side is nil, then it's going to be true. Then that means we do have a leaf node there. So sum of nodes 0. So then that means we need to do target value minus root dot value, right? And then we need to check if it's equal to 0. So if this is going to equal to 0, and we also have, and it's also a leaf node, then we would return true. If it is leaf node and is sum nodes 0, then return true. Then we can just do an else here. Else we gotta look left and right. So just traverse the whole tree. Left equal. Alright, cool. Then we just do return left equals sum or right equals sum. And now we can see that our value is false, false, false. Okay, that's not good. I guess I have to make these local variables for some awful reason. Sorry guys, I didn't know that was a problem that Roblox had to deal with. But yeah, it should be working fine now. Hopefully you guys learned a lot. That was the whole path sum depth first search algorithm, and I'll see you in the next episode. Goodbye.